Okay, okay. Today I will talk about a double free, which is I feel that it's a special case of use after free. So I will first do a quick recap of use after free so that we can have the background knowledge. Eh, Okay, this one is our program from last session. So today I will uh use the slides as the whiteboard. So that's why it's so empty now. Also because I didn't have much time to prepare. I Okay, so this one is our example from last time. So actually we have a struct. It's like this. So if you are not familiar with C, struct in C is like a class in Python or Java. So you can have a few different variables, or more properly we call them fields. Fields field in a class. So there are two fields. One is eight a character array of 8 characters, and one is a long. So this. Then after that we have, okay, let me make a copy of this. So we can allocate the struct. So I won't repeat the differences between stack and heap because that will take a lot of time. But I will just quickly show how we allocate. So here we can allocate a car in the heap. So like this. So what I'm doing here is just allocating the size of a car. So in C, we always have to put struct in front of the structure. That's the syntax. You can make it shorter, but I will keep it like this. So we allocate, it should be big C. So allocate size of this struct, and then it assign to this pointer. And then after allocate, in C, usually you should free the memory after you don't use it. Otherwise, you'll have memory leak. So memory leak is when you see in Task Manager, your program use a lot of RAM. That's because there's the maybe the program they allocate a lot of memory, but they didn't free. So the program it used up a lot of memory on your computer. That's why it's very important to free. But one problem that happens if you don't when you free is if you don't set this to a null pointer, so to 0, to clear away. If you don't have this, then car will hold a dangling pointer, because this pointer should have been freed already. It doesn't, it's not supposed to be used anymore. But if you forget to set to 0, and then let's say you have another different object, uh different car, then now if we look at the pointer that are kept by these two different variables, you will see that they are the same. Uh, You see, they have the same pointer. So now these two things point to the same object, but it was probably not the intended behavior. Okay, so now I can illustrate this on the slides with some visualization of the heap. So let's say this is our code. Yeah, open like this. So syntax highlighting. Okay, this is our code. So we have three things. One is car, or we call this car one. Car one and car two. And we have one more thing called the free list, which I also talked about last week, last session. So now we go through the code one by one. So first we have allocate. So when you allocate, car one now has is given this piece of memory. Put it like this, color, blue color. Right? Then after that we free, then this will be here in the free list. And then now allocate again. The when you allocate again, the allocator will allocator will find a chunk in the free list. So because these two are the same size, these two have the same size, so it will just reuse this chunk for this car. So, but because car one didn't clear the variable, the pointer, so now they both share the same chunk. So when car two is changed, car one will also change. So if you think about this in other programming languages, you think this is like pass by reference or shallow copy. And sometimes when you may have mistakes in your program when this happens. But this is still okay for now. And last week I also go through how you can override a function pointer. You can, if the struct has a function pointer, for example, this one. Oh, okay. Yeah. I removed, for example, if the struct has a function pointer and it has the same size as a different struct, then maybe you can use outer free to share the same chunk by two different objects. Then when you modify yearboard of a car, because it's shared with a mule, so you can modify the function pointer and get RC. So this one was covered last session. Other than that, you can also corrupt the free list, which is has the implementation is specific to the allocator. So for Linux, the allocator is, I think, is ptmalloc. So you can corrupt how ptmalloc maintains the corrupt the free list, then ptmalloc let ptmalloc allocate a chunk at a memory location that you want. For example, what we did here is we allocated a location, a pointer to a location that we want. Then we overwrite it to get RCE. So all of this is covered last week, so I will not repeat. Now I'll talk about double free, which is, I feel that is a similar concept to use after free. So let me do a quick code example. So let's see what happens here. So now we don't have this, but I free it 2 times. Okay, if you didn't attend the last session, it is okay. I think you will still be able to follow the content today, so don't worry. Wait, you see, when I run this program, it says double free detected. So most of the allocators, they will detect if there's a double free, so that they can prevent attackers from exploiting the program. But later I'll show how it is still possible to bypass this quite easily. So let me show the again illustration of what is going on in the slides. Okay, here's your code, and then look at the free list again. So first, we allocate a car, and then next step, free a car means this comes to the free list. But we forgot, but we didn't set car equals to 0. So car still holds this chunk. Then now free again. And we have the same chunk 2 times in the free list. So you see how this is very easy to detect by the allocator. Very easy. You just go through the free list and see if there's repeated chunks. But now we can pause a bit. Can you think of why there is a problem when you have 2 of the same chunks in the free list? Okay, give you all some time to think about it.
Maybe both chunk will be overwritten, overflow, but I don't know.
Oh, so if your operations on the chunk is safe, then there won't be overflow. So we don't need to worry about overflow here.
If the next malloc happens, right, if you take the one chunk from the free list, then if any data returned to the next malloc struct, then the data in the free list, the next data, the second one will be returned as well, or not.
Yeah. So that is the problem of double free.
Oh,
So yes, yeah, you're correct. So now we make this code a bit longer. Let's say we have another allocation, 2 more allocations, 2 and 3. Okay, then let's say we did it correctly and we set car equals to 0. So now this one, okay, after we come here, this one is safe already. But we also have 2 more upcoming. Car 2 and car 3. See, when we allocate to car 2, we'll take from the free list. Yeah, so it's exactly what you said. When you allocate from car 3, take from the free list. Then again, they are sharing. You have 2 pointers sharing the same object, same object, which is not what you want in a program. So this is the bug. So you see, it's very, very similar to use after free, because use after free, you have 2 sharing the same chunk, and double free also the same problem, 2 sharing the same chunk. So the outcome is the same. And another reason why I think they are the same thing is because if you think of free, now is not use after free, but it's free after free. But if you think of free as a use, if you are using it in a free, if you think about it like that, then you're also using after free. That's why I think it's I call it a special case of use after free. So now let's see. Now we can see that the concept is about the same. Once you get this kind of situation, you share the same chunk, then the things you can do is about almost the same as use after free already. You can just watch the first session already, and what you can do from there is you can do the same thing. But let's look at this problem now, because it says double free detected in Tcache 2. Well, actually we can find this in the source code, but sorry, I forgot to save the link, so we have to go and find it again. Hopefully I can find it fast. Oh yeah, I can. Yeah. Let's go to how to hit first. I wanted to show one of the, yeah, it's this one. No. This one, House of Block Cake. So we'll go through this demo. I see. Yeah, so they have the link here. Okay, let me put it here. So you come into the Linux, this the Git, and we can find press diff. So this is the commit to prevent double free. So let's see what they do to prevent double free. Okay, so if this is your first time looking at Linux commits, I'll go through them also. So first is the change log to just say what they changed. And then we can come here. Is it this one? Okay, this one you see is just a test case. You know, this one also test case. So only got this one. So this field exists to detect double free, this key. And then E is a Tcache entry. So it means E is a struct out like this. Before that, there's just a next, but now there's an extra pointer called key. So the Tcache entry contains a next and a key. And here we want to set key to be Tcache. Not very sure what is Tcash here, but we move forward first. So maybe you don't need to really understand the code, but just read the comments. First, we check if, okay, wait, I think it's better I show you all. See if I can expand. Okay, ah, this, okay, this is the whole code. So this is free. So you see free, free. So this is free. But they have an in front, but this is not so important. So what is P? So AV is, I think it stands for arena, but I am not sure. Then tongue pointer P is just this, our what we ask it to free. And then have lock. So why they check if they have lock? Because Tcache stands for thread cache, thread local cache. So if you know multi-threading, this is for to optimize multi-threading. And if you know multi-threading, usually you need to have locks, mutex, these kind of things. So this is just sharing with you all these small details when you read the source code. Yeah, this one let me check. Okay, never mind. If you are interested, you can go check yourself. It's not important for us now. But most important thing is this chunk to map. If you are reading source code for allocators, you'll see this a lot. Because let me show you what is a chunk in mem. So chunk to mem. So usually when we allocate something, an object, let's say a car again from our example, this is what the programmer sees. So, yeah. So the programmer sees this. Then let's say the pointer to this is 555, okay, 5000100. This is the address of this. This is what the programmer sees. Wait, let me make it 120. But actually, this one just contains the contents of the car. So let's say we look at this example. We have a owner and a yearboard. So inside here, we have owner and yearboard. These are the variables, the fields by the programmer. But you know the allocator also needs to keep track of extra information to maintain the free list. Because it needs to know, because you see the free list is a linked list. It needs to know what is the next. In a free list, it needs to know what is the next chunk in the free list. So, like, for example, like this. So in order to have space to in order to have space to set all this extra information, it actually allocates an extra small space up here that is starting a bit before. So here there'll be next, and previous. Okay, this is not very accurate because this should be 8 bytes, 8 bytes. So like this, for example. So 10 is 16 bytes. So let's say this 8 bytes, 8 bytes, and so on. And then this next should next point to here. It is. So to the allocator, this is a chunk. This one is a chunk. And mem is just here. So okay, I here like this. So if we find the source code for chunk to mem, you see it is just the pointer. Okay, so chunk to mem means if you are given this address, because this is the chunk, then you just want to get the memory of the object that is used by the programmer. Then you just add a constant offset, and the constant offset is chunk header size. So the size of the header. Let's see, what is this? This is 2 times. What is size? Size is, okay, you see, oh, it's just here. Then what is this? Size of size t. Anyway, this is, so is what I show here. 2 things. So the chunk header has 2 things inside. That's why chunk to mem, you add 2 times chunk header size. Okay, let me put this here also. It actually is just up here. They are the same link. 2 times size. Okay, let's go back to the source code. So now we know what is chunk to mem. E means we are at checking this, but never mind, we don't focus so much on the objects, we just read. So here you see, this test succeed on double free, blah, 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 but we don't trust it 100% because it might be the random payload data. Payload data means user input. Because you see, actually it is part of the user input. So it could be user input that matches because actually the header, the metadata is not just 2 pointers. There are 2 more things. So you can find glibc chunk header. And you see there are more things. There's a okay, yeah. What I show there is just this one is just example. It's wrong. This one is the correct one. Malloc internals. If you are interested, you can read more. There are more things. Blah blah. Then forward. You see, this is the next. So actually, the chunk starts here, but the next is okay. I think I might be giving wrong information, but basically they are saying that it might be user input because it do chunk to mem. And but let's continue. You see here for loop. This, if you are familiar with linked list code to do linked list, you see it's very straightforward. Just get just not very sure. Actually, I'm not familiar with this, but it's like linked list code. You just keep going to the next one, and then you see if it is equal to the one that we want to free. The P is what we want to free, the chunk that we want to free, and the E is the chunk to mem. And then you check if it's the same. If it's the same, then means that you are freeing the same object. Okay, maybe I took too long on this, but I hope we have spend some time together looking at the source code so that we understand exactly what is going on and not just based on what I tell you all. So now we will look at how to bypass this check, because it looks like this check, if you only read this part and you don't know more things, it feels like this is very secure. It will prevent all the double free, but actually it doesn't prevent all the double free. So okay, this one is the House of Bot Cake is the example that we will look at, but I will use our own code first. Okay, so let's see what happens in the free list every time we free, and we will do it 7 times. Actually, we do it 10 times. So I will put a breakpoint before we free at the start, and then after every free. Hmm. Okay, run. We have breakpoint at, oh, let me compile with debug symbols. G, oh, sorry. Uh, this is our code. So now I equals 0. Actually, we were here. Our breakpoint is here. That's why the arrow say the next thing that we will execute is this. So let's look at the heap bin. Tcache bins are empty. Then you see, actually, there are other bins. There are fast bins, unsorted bin, small bin, large bin. So this is why the protection is not enough, because there's a limit to the Tcache bin. Once the Tcache bin is filled up, then we will start using the other bins. And then when we use the other bins, the protection is not there already. So let's see. Continue. Wait, I cannot free the same. variable because you will get the double free error. Use the array and allocate. Okay, we allocate first, and then we free one by one, so that we don't have double free now. We have 10 pointers. We allocate one object to each of them, and then we free them one by one. Now let's look at the heap bin. All are empty, but heap chunks, we have 10 chunks. So now we continue. We reach here. Yeah, we just executed this one. Then we count one to next. Next, we will come here again. Now we look at heap bin. One chunk. Next. Two chunks. Next. Three chunks. Next. Four chunks. Next. Five chunks. Next. Six chunks. Next. Seven chunks. Next. So Tcache bin only holds 7 chunks. Let's look at the source code again to confirm this. Yeah, I'm not very sure what it is. You need to read other write-ups or read the code yourself to know. I think any CTF player that plays Pwn would know, but I'm look. I think it's this one, Tcache count. Okay, not very sure where to find the size. Yeah, if you want to find, you can try to find also. We try to find first, see if you can find. Should be this because you see when this is the free. So see after this part, see this part is Tcache for Tcache. If we don't successfully return here, means that we haven't free yet because the Tcache bin is full already. Then now we test the fast bin and see if we can put inside a fast bin. So fast bin is fast because it is a bit special. So fast bin is fast. Then unsorted bin is, I think, it's the slowest. Then small bin is middle. Then large bin is a bit slower. Then fastest, then faster, then faster, slowest. So I think it's this one. Never mind. So the important thing is there's only 7. 7 is the maximum, and then after that it will put inside fast bin. So we let me share a bit about fast bins also. Fast bin, you see there are 7 fast bins. 0, 1, 2, 3, 4, 5, 6, 7 fast bins, and each one have a size. So objects of different size will be put into different fast bins. So if you're because our car is just hex 20 the size, so you put into the first fast bin. If you allocate bigger, then you put into the next fast bin, or so on. Then if it's too big to be here, then it will be one of the other bins. So let's see if you can find this here. Small fast bins, small chunks are stored in specific size specific bins. Then Okay, the rest you need to read more and learn more. So the people that do exploit writing, either in CTF or bug bounty, they have to have quite good understanding of this because you need to know where your chunk goes to after you free it. But if you are just doing very simple exploit, maybe you just need to know the concept a bit lah, and then go and learn about the details if you need to. So this is the case for glibc for Linux. Then for other OS or other allocator, because there's another allocator called JEmalloc, which is used by other systems. And then Windows, of course, they write their own heap also. So if you are very pro at this, you still need to learn the structure, the allocation details for other heap for other systems. But once you know one of them, it's very easy to learn the other ones. Like for example, I am not expert at Linux one, but when I see this, I can have a good idea of what they do. Yeah, there's a lot of things to read, so you can read all of them if you are interested. But now we come back to here. So we have freed 8 chunks. Now we are on our 9th chunk. And so on. So far, everything is okay. There's no double free, and we managed to free until here. So now let's see. I don't put a breakpoint. Now let's see if I do a double free on one of the cars. Free car 0. Double free detected. Because car 0 was the first one to be freed, so it is in Tcache bin. What about free car 6? It's also in Tcache too. But what about I free car 7? This is the 8th car. You see, now I can free again. Okay, in fact, let's look at the look inside the debugger, and we will see it. Heap bin. See, this is the one that we just freed. This one just so the one that we just freed is at the start of the linked list. First in, first last in, first out. So this one we just freed, and is it the same as the one we freed earlier? So we have double freed this. So let's say we allocate again 3 more times. So we allocate 1, then 2, 3, wait, 4. So the first and fourth will return the same chunk. Let's see if that is what we get. Wait. Okay, I think this is another protection. I think it's another protection. We try free a different one. That is not the first, not the last one of the free list. But I think it will fail. Okay, there is another protection. You cannot. Let's see what is happening. Why? Okay, let me put back to. Let's put a. Okay, after the first free, first allocate, we okay, this one got tell us. Maybe there should be less here. Let me see why. Oh, because they give us from the T-cash bin first. You see now there are only 6 chunks here. My bad. So if we want to get this, we need to take everything out of the T-cash bin first. Then I think okay, you see the malloc consolidate error. If we continue, you see we skip all the breakpoint already. And we still don't get the malloc consider this consolidate error. We haven't gotten this yet. Until we return. So only after we return from main, this happens. So this is because I think it's the part of the cleanup. We don't spend too much time on this, but it's part of the cleanup that the program is doing. It's not related to double free, but it happens because you have double free. Okay, now we quickly allocate everything in this first, just to take everything out from Tcash bin. Okay, so now we are here. After this, we see that, I still got 4. Let me see. Okay, we're not very sure why. Okay, can print REX, which should be the return value of malloc. So C3C0 is here. Okay, I think I know why. You see here, you see count is 3. I think we mess up the fast bin already. No, we are still in Tcash bin. Wow, I also quite confused now. Okay.
Is it?
Hmm?
Not sure. Why less than 7 or 970?
This because in the Tcash bin got 7 chunks.
Oh,
Then I want to take everything out of the Tcash bin.
okay.
Actually, I can look at this to see what they do. Okay, but we don't look at the answer first. Okay, now I want to check what happens after 7 to confirm my theory. We are at line 82. Oh, compile, run. While we are still here, I think I need to restart. Eh? Oh, it's line 82 not. Oh, yeah, because it's all comments. Skip already. So we finished this 7. Hit bin. See, after 7, we have 4 in the fast bin. Because all the 7, we free 11 in total. And there were 7 in Tcash bin. So we take out 7 from the Tcash bin. Now we have 4 in the fast bin. Let's see what happened after we take out 1. Okay, this one is this breakpoint. Then we continue again. Oh, so I think what happened is they will move everything to the Tcache bin, maybe a type of optimization. So after we run again, first everything is in fast bin. Then after we allocate one, it move everything to fast bin. So let me. So this one is chunk 7, car 7, because it's the last one that we freed. Let me see if I put car 8, if we will have any difference. So again, so this time this one is car 8. So you see, this is car 9. Okay, 1, 2, 3. Okay, so now there's one less because, wow, this is very confusing actually. Yeah, every time this. I should print out. You look at heap chunks. So this one is car 0. Here, somewhere here, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So car 8 is the one. So car 8, because this one is 9, then this 8. Eh? 0, 1, 2, 3, 4, 5, 6, 7, 8. This one is 8. Car 8 is here. And then before car 8, it is car 9, which is this one. Then before car 9, we free car 8 again. Then before car 8, we free car 7. But it's no longer here. So, so it's not, I think it's first in, first out, not last in, first out. So car 7 is not here already. And it should be this. Let me print this. Okay, we are here now. So where's my output? I need to set this. If you use GEF and your output is gone, you need to set this so it doesn't clear your output. Okay, so this is what we get for car 0. Let's check bins, chunks. So 0, 1, 2, 3, 4, 5, 7, 8, 9. So car 8 is the last one that we feed. And then before that is car 7. And before that is car 8 again. But we take out car 9. Okay, actually no. Okay, so I think this is confusing because what happened is, I got confused also, but let's roll out. Okay, we will end once we finish this because don't want to take too long. Just try and wrap up what we are doing for double free. Okay, let's say free list is in the fast bin. Let's see what is in the fast bin after we free everything. Okay, 3A0. Then three C 0, 3A 0. There should be more. Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3A 0, 3C 0, and 3E 0. Okay, actually one more here. Okay, before we free card it, we have 3C, 3A, 38. Oh, 3C, 3A, 38. And then when we want to free card it again, card 8 should be 3A 0. So we will put here. But I think when it tries to modify the linked list to be like this, it somehow breaks this accidentally. Because, oh, yeah, you see here, say loop detected. Because it keeps track of the front and next and previous pointer. So before we have this, we are like this. But after we free again, then we put this in front. But this, it also needs to record what is before it. And because of this, these two are the same thing. They are the exact same thing. So let me put different color. These are the same. Then see, if this before this should be this, then with this, sorry. Now we have to, this one cannot anymore because this one will remember that before this is this, and then so on. So we make a loop in here by freeing car 8. But if we free car 7, it's a bit different because if we just free, instead of freeing this, we free car 7, we free this again. Then we put this in front. If we put this in front, then it doesn't, if we put this in front, the previous pointer is updated this, but it doesn't affect anything. It just forms a loop again. So now it's like this, but these two are the same thing. So there's again a loop. Like this. Okay. So this is why when you do double free, it'll be a bit confusing. So now I don't want to free so many. I just have 8, 9 and 9. So that we only got 2 in the free list. It makes it not so complicated. Okay. Run. Okay, after free everything, we got 7 in the. After allocating everything, we got 7 in Tcash bin, 2 in fast bin. Then we take everything out of Tcash bin. Now we only got 2 left in fast bin. Oh yeah, but we don't have double free. Hmm. Wait. Okay, this one fast bin because the last one that I free here is car 8. Last, then I free again. But it's too obvious already. The fast bin can also know that it's double free because it's the latest one that was free. So they still have a bit of protection. It's called fast top because it's the top of the fast bin. So instead I free car 7. I run. We are here. Hit bin. It's car 7, car 8, car 7, and loop. Okay, loop. After free everything, yes, fast Tcash bin empty. Then now we come here, set breakpoint here. Let's see what is in the car 0. It's 380, which is the first one in the list. And then next, if we allocate again, we will get 380. Then if we allocate again, we should get 380 because car 1 gets this, and then car 2 gets this. So hopefully I'm correct, but maybe there will be problem again. Okay, now it crashed. Well, let's see why. Okay, we are at here. So let's see what is the hit bin. 380, 380. Continue. Bin. Now it's 380. Breakpoint here. So we break here. Then you see hit bin got 380, 380, and 380 because we allocated 380. And come here, hit bin again, and I print REX, which should be the return value of this. So it's 380. The next is 380 again. Let's see if we can get it here. We reach here. See if we printed. So car 0 and car 2 got the same. So it worked. So we managed to exploit a very basic exploit for this double free to get 2 pointers to point to the same memory. Yeah, I will stop here for today. I quickly go through this one. So the basic idea here is allocate 7 chunks to fill up Tcache lists. Fill up Tcache lists, and then they do something called consolidating. So this one, I will talk about it next session. I'll go through this exploit the next session. Consolidate two chunks together means when you got two chunks, they combine them together, because actually you see they are next to each other. 380 and 3A0 is just 32 bytes apart. So they will combine together. And then you see, if you combine two together, it's a bit like you can do overflow, because if you allocate a big chunk, if you allocate overlapping chunk, it means you control two chunks at the same time. But because another chunk may only take this later part, so you overlap and you override a bit, overflow a bit, like this kind of concept. But we'll go through that in more detail. We'll go through a demo of this in the next session. So they do chunk overlapping. You see, they take out of Tcache list, blah blah blah. Another special thing, if you want to try this yourself, is the important thing is they make a very big chunk. So this hex 100 for our one, our size is just hex 20. Hex 100 means they will put inside one of the which bin, unsorted bin. They put inside unsorted bin. Unsorted bin will do the consolidating, means combine two chunks to be one chunk. Because fast bin, it must be fixed size. And I think small bin and large bin also have certain size. Okay, I'll stop here. Next, part 3, we'll look at this, how we can, because now what we have is just we share the same memory for two different pointers. Next, we'll look at how this one can be used to give us over arbitrary write, so you can write anywhere in memory. Yeah, today we still overshoot 1 hour. I was hoping we can end earlier. Okay, any question?
I would like to ask.
Oh,
So the demo here is specific to the glib version, or it works on all glibc version.
oh, so no, it doesn't work on all version, but it should work from 2. So for this one, work from 225 onwards. So my glibc is 235. So it worked 225 onwards until they make a patch, then it doesn't work anymore. So the people who are active in this area, they will keep track of the commits.
I see.
Yeah, that's why the heap pwn harder and harder every year, because there's new mitigation every year. At the start, when I start in 2017, there's not even Tcache. But actually Tcache, they say make it easier. But before that, it was also, there's other older attacks when I was learning at the start. For example, there are some you see before 229, so cannot work anymore. Before 229. A lot of things don't work anymore already. They don't work really.
So every version come out, then they try to develop a new bypass, then they name it using the house.
The house is, they give a name on it's just everyone, you see, when they house of water, house of what, the name is just usually related to the CTF challenge or the person that come up with the bypass.
Oh, okay.
Yeah, but looks like every time when they come out with a new patch, then people can still bypass lah. Because actually it's very hard to to block everything also. You can always come up with a new way to bypass it. But means you have more restrictions. For example, here we have to allocate 7 times and we cannot have loop and blah blah blah. Oh, actually loop is okay. Loop in the free list should be okay.
Okay, thank you.
Mhm. I think actually I was thinking maybe this whole year every session will be about hip because there is many things that I can talk about and I cover only a little things every session. You ask does yeah, this repo how to hip is a good resource for learning hip. So not only UAF is just one kind of bug. Then there's also overflow. For example, here there are also resources for overflow. Some of them UAF, some of them override, some of them double free. But I think if you have UAF, it just means you have double free now because you can free the same thing again.
Oh, one more question. Sorry.
Mm.
So, if you have double free, right, and then if you control any one of the chunk,
Mm.
then how it leads to RCE? Is it like the previous session?
So previous session I showed a way to RCE, but I also forgot what is the way already. I need to watch again. But for double free, this house of block cake is one way to get RCE.
Or he just do some magic and then
Yeah.
oh, okay.
So all of this is to show how to get arbitrary right. So for arbitrary right, you can
Arbitrary.
get RCE from arbitrary right because you can write to return address or write to function pointer or global offset table. So usually the idea is to let malloc give you an address that is not part of the heap. It's part of stack or part of other things.
And
So
it's
like
not part of the heap.
yeah. So last session we actually I really forgot what is the let me find. Last session is this guy in taxi nightmare. This one the outcome is we get malloc to allocate an address to the stack by modifying the free list, the pointers. So the idea is like this: you got the free list like this, then this is the basic idea. Then usually people will use this idea in the exploit, adapt it to to the allocator. So for example, you got free list like this. Then if you got use after free or you got overflow, you can modify the pointer because the pointer is stored in the chunk which we showed just now. Modify this pointer to point to something else instead. For example, somewhere in the stack, like this. And then after that, you malloc, take this out. But now, after malloc, this is the next one that you get. Then you get to write to here already. But this is not part of the heap. This is other parts that maybe contain function pointers.
So there is no such thing like allocate shellcode into heap, then execute from there. Because you say they usually point to the stack. Because I only learned about Stack Overflow a little bit. They usually like overflow the stack and execute shellcode from there.
Oh,
Then there's no such thing in heap like heap. I mean,
so the heap one, you can make it similar to the stack one. If you can find out the address of your stack, then you let malloc return this to be your stack. So your stack pointer, RSP. Then when you write into here, it's the almost same concept like you doing Stack Overflow. So then you reuse the same techniques as Stack Overflow. But you cannot write in shellcode in the heap because the heap will not have executable permissions. For example, see here, RW. But actually in the stack also, there will not be executable permission. So, but if you do the easier challenges, then there will be. Then after that, you have to use, you have to do ROP to exploit because you don't have executable. But so the concept is you can reuse the concepts once you get your arbitrary right in a stack.
I see. I have no question.
Okay.
No other question. Thank you.
Welcome.
So, anyone have any other question? If no, I think we can end it in 3 minutes.
Or I check if everyone's still following, because next week, next session, we go
It will be
through
harder. I
this
think.
one. Yeah, then
Because
I cannot keep doing recap. If I keep doing recap, then we'll always end at 10 to 10:30 already. Okay, just like everyone is okay. Then we will look at this one next session.
we have recording. No worries.
Um,
I think I can stop the recording.